happy to have Reuven Balkin. He got PhD from Munich and then was at the Technion, and now at the Santa Cruz, our neighbors. And then we are happy to have him here to tell us about probing light scalars with dense stars.
Thank you very much. Thanks for inviting me. I'm very happy to be here. My first time at UC Davis. So today I'm going to talk about how we use dense stars to probe light scalars, and this is work based on a couple of papers from the last couple of years with my collaborators Konstantin Springmann, Avi Serra, Stefan Stelzl, and Andy Weiler. While we started all of this when we were all together in Munich, and since then we all spread out, except for Andy, who's stuck in Munich. And I'll spend most of my time talking about the last two papers, the more recent one, but I also mentioned the older ones at some point, briefly.
You make it sound like it's bad in Munich.
No, it's fantastic. It's amazing in Munich. And just for everything, just so everything is coherent with everything that's going around. This is a light Halloween-themed talk. Not too much, just little touches here and there, not to make it overbearing.
I like your costume.
Sorry?
I like your costume.
There's like Halloween with an emphasis on pumpkin. So this is going to be like the little thing throughout. Alright, so I'll start motivating. So there are a lot of searches for feebly coupled light physics. One way we tried to do, community tried in the past to look for heavy physics. Nothing came out in the LHC so far. And then a lot of people started looking at lighter scalars, which are very weakly coupled to the standard model, and it's motivated by a number of beyond the standard model scenarios. Maybe most popular is the QCD axion and generally Alps. There were relaxions also. So one way of probing this type of physics would be, for example, to assume it's dark matter, and then there are many ways of trying to probe its interaction with the standard model. And what you typically assume is that you have some operator, some interaction between your scalar, dark matter in this case, and the standard model, and you activate the environment. You assume it's dark matter and it's around you, and then you see how the standard model reacts, and you try to find effects coming from the fact that you have this, that we're inside this environment of dark matter. Now, of course, it's also useful to think about probes that are not dependent on the abundance of this new scalar field. For one, it might not be dark matter. It could be some other field that has nothing to do with dark matter. There's also the kind of depressing possibility that it might be dark matter, but maybe we're kind of accidentally, unfortunately, living in some under-fluctuation of dark matter around us, and it will be very hard to see. So there are a couple of probes you can use that are not relying on the dark matter density or the relic abundance of this particle. So fifth, fourth, and stellar cooling, to name a few. Typically these are relevant when you have a linear coupling. But what I'm going to talk about is probes that use environmental effects, and in particular I will talk about baryon density, finite baryon density. And it's like the complementary picture. You turn on some standard model background and you ask what happens to the beyond the standard model fields, and if there's any way of seeing it and probing it this way. So I'll sketch a little diagram to show you what's kind of the philosophy. You turn on the standard model, you have some background, and again, in my case, it's going to be baryon density, unless I say otherwise. You turn on this operator, this would change the properties of new physics. It could be changing the coupling to standard model. What we're going to be focusing on is a situation where this could lead to a phase transition, meaning that the field itself gets some background value, and I would also refer to it as sourcing. Then the question is, once I turn on the same operator now operating in the now in some background of my beyond the standard model field, the question is this observable? What's the back reaction on the stuff we can actually see, which is stars in my case, whatever standard model system you have in mind. So this is kind of the broad philosophy, and we'll see later how we apply it in our case for stars. Okay, so this is the motivation. As far as what I'm going to talk about, I'll start with just giving a broad refresher on what are stellar remnants, and which will be the focus of this talk. Then I'll go off into like a nice simple example of how we use white dwarfs to probe so-called lighter QCD axion, and I'll of course explain what I mean by lighter QCD axions. Then I'll kind of take a step back and widen the perspective and look at more general models at neutron stars and what we hope to learn from that. And then I'll mention these couple of older papers that we used similar approach to probe or to say something about the QCD axion and relaxions, and then I'll summarize. So, stellar remnants. In particular, I'm going to talk about white dwarfs and neutron stars. So, I want to get you excited. So I looked for a very cool computer-generated image of a neutron star. It's not a real neutron star. It's some computer generated this, but it's really nice and cool. For white dwarfs, you can actually have a picture of a white dwarf. So this is Sirius A, known also as the dog star. And then there's this little blip here. That's a white dwarf. Sirius B, also known as the pop star. So that's a real image, but it's not really cool. So I also add a white dwarf from a computer-generated image, which is much, much cooler. So I have this in mind to keep you motivated. And as an added bonus, I did, at this point almost mandatory AI-generated image of a pumpkin star. So this is a pumpkin neutron star. So these are the two objects we're going to talk about. What are they? They are endpoints of stellar evolution. So sun, a star like our sun, various masses would evolve and at some point reach the end of its life when it cannot support gravity by nuclear processes, and then it would typically collapse, either more violently or less, depending on its mass, to some other configuration. What is common to both of these stars is that gravity is balanced by the degeneracy pressure, and I'm going to work in the limit where the temperature is much smaller than the chemical potential, so I can essentially set the temperature to be 0. And I'll do a simple estimation to understand kind of the properties of these stars. So I'm going to assume that the number density in the star is given by the chemical potential. The Fermi energy is just the number of particles and their typical energy, which is again the Fermi energy, and now I'll use just the fact that I know the number density and the size of the object to write this as r cubed times mu to the 4th. And what I need to compare it is to the gravitational energy, which is given by the expression there. The only thing that one needs to notice here is that I assumed, which is the case for both of these stars, that the gravitational mass of the object is dominated by the rest mass of the nuclei. So this really turned into n times the number of nuclei. This is true for both neutron stars and white dwarfs. Now when I equate the Fermi energy and the gravitational energy, I get a result for how the radius should scale, and this would depend on the chemical potential. Now for a neutron star, the degeneracy pressure is the one from the neutrons. So that's why I'm setting there the chemical potential for the neutron star, and then you get the neutron mass, and then you get something like 10 kilometers. For a white dwarf, the degeneracy pressure is generated by the electrons, so you get almost the same, but with this factor of 1,000 enhancement, so you get around 10 to the 4 kilometers. For a white dwarf, interestingly, their mass doesn't depend on mu, and you get something that is equivalent to a solar mass. So in both cases, one should appreciate how small these objects are compared to how massive they are. You take the sun, the mass of the sun, and you shrink it either to 10 to the 4 kilometers, which is much smaller than our sun, so it's much denser, or even more extreme, 10 kilometers, which is really, really insane to think about such a compact, dense object.
Can you remind me? I mean, what is the picture of a white? Why does a white dwarf shine? I mean, it's shining into the visible spectrum.
It's just leftover temperature.
Yeah, it's leftover temperature. It takes a long time to get rid of it because it's very inefficiently cooling, and they hypothesize that at the end of its life it becomes this black.
Okay. Okay, so it's just a residual
Yes.
effect. Okay.
Why is the number density to chemical potential to the power 3 like why are they related that way?
So I would say that you can write the number density as a function of the Fermi momentum, and the assumption here is that the Fermi momentum is, that the energy at the Fermi level is essentially the mass of this particle. So that's all I'm saying is that there's one scale in, the microscopic, the only thermodynamic scale of interest here is the chemical potential. That's the only thing it essentially sets everything, both the number density and the energy of each particle in the system.
I know chemical potential is about particle number,
So chemical potential for me is, how many levels I populate, how many states I integrate.
And EG is what again? I know that's
EG is just the gravitation, the gravitational energy. So you get this like from Newtonian gravity.
So you set those energy levels equal to each other in the
Yes.
sense of populating these states?
Just that the energy, it's like equating potential energy with kinetic energy. You have these two energies that have to be at the same order for this object to be stable configuration.
Okay.
If you found the minimum, there would just be some factors of 5 and 3. So
Yeah.
neglecting 5/3.
Yeah. All of this up to order 1 also factors of 1.
Gravity wants to shrink it, that would increase the Fermi energy. These things are balanced, going opposite directions, so they balance when they're roughly equal.
Like for that balancing, I use force, not energy. So.
Yeah, but that's
If it's a power law, it doesn't matter. If it's a power law, depending on the parameters.
I mean, you can see it also by the scaling with R, yes? I mean, they both work in different directions, and maybe some sweet spot when the two are the same.
the force is just
exactly
the derivative.
Yes.
So.
Force is the vector potential. So how well do these estimations, which we have here, how well do they sit with experiment or observation? So this is some old plot I found for white dwarfs. You can see here what we will see a lot in this talk is a mass radius curve. So the x-axis is radius in 10 to the 3 kilometers. The y-axis is the mass of the object normalized to stellar mass. The points there are observed white dwarfs. And these curves are the prediction of a particular model, which is used for white dwarf, which I'll tell you in a second what exactly it is. And the only difference between this curve and the other curves is just the temperature. So here you have the finite temperatures effect pushing this curve up. And then I think this one is already the next one. And the last three are really on top of each other. So it kind of converges quickly to this essentially t equals 0 curve. And what you can see is that all the observed points are sitting very comfortably in this range. And, these are the least dense stars. They are the largest or the least dense. And it would make sense that here temperature effects are the most important because it's an expansion in mu over t, and mu is the smallest there. So it's not a surprise that here you can get this, this scattered observations, while here they all converge quite quickly as they become more dense, and the temperature plays a smaller role in their, in their structure. So that works pretty well, and again, you kind of get 10 to the 4 exactly here. Yeah.
Can I ask, you don't, presumably not measuring, you don't directly measure either the mass or the radius, right? You measure like the luminosity and the redshift or something like that, right? You measure two other parameters, then you infer these from the theory, but then you're using this to test the theory. So I'm not quite understanding. Wouldn't this success just be built into the model?
Good. So it's an excellent point. So this is some old plot that I found just because I wanted to show the scaling, that the scaling works. I have another plot later on where we took data points a bit more carefully, and we were trying to the best of our ability to find the people that did an analysis which was independent, so that exactly did not do the procedure that you were suggesting, which does, it's very common that you measure one of these things, the mass or the radius, and then under certain assumptions you infer what the other one is, which is exactly what we want to probe. So you want an independent measurement of both. So it's true, even then there are still some assumptions when you're measuring the luminosity and assuming what's the radius. Typically there are some assumptions about like the atmosphere and how this thing has the structure of how the luminosity gets to you. And so it's true, and we were kind of careful later on to find points that independently measure the mass and the radius so we can really probe the relations between them and not assume it.
Because you're going to somehow argue that if this breaks down too much,
Yes.
then that's a constraint,
Correct.
right? So that's
Yes.
actually kind of going to be
Yes.
the point, I think,
Yes.
right?
Correct.
So for Sirius B, do they have some interferometry to infer the radius?
I think they do. It's also the closest one, so I think they could have very.
So they
very
can
good
somehow like measure what? Like, do they measure the surface gravity, or what do they, because of redshift?
Hanbury-Brown twist interferometry.
Uh-huh.
And what do they measure? Like, what physical parameter of the star does that tell you? The temperature or
Size.
the size?
The
Because
size is inferred from the luminosity, but typically
Yeah.
because these are not perfect black body objects.
But that's in some sense the relation that you're, well, maybe it's not directly, because the luminosity is the temperature, which you're sort of, anyway, go
Yeah.
on. I mean, we're never, yeah. There's always going to be some question about these things, right?
Yes, and we're not astrophysicists,
Yeah.
so we're trying
Yeah.
to understand our best what people have done. So these are, as I said, these are explained by a particular model called the Chandrasekhar model, which is also the name of this very famous limit, which is how massive a white dwarf can be, or an object that is supported by electron the density pressure can be, which is about 1.4 solar masses. And this is a plot I took from a recent review just to kind of highlight where we are with respect to neutron stars. So this is again radius in kilometers, mass in solar masses, and these areas are different observations for different neutron stars that are measured in different ways. So again, we're kind of, as far as the scaling, we're in the right ballpark, okay? So 10 kilometers, about between 1 and 2 solar masses is kind of where we are. You can see that there are a bunch of other lines here. These are all, again, some prediction depending on your assumption on the microphysics. And I'll show you a plot later which even shows, a much bigger zoo of these curves, which reflects how little we know about dense matter in nature, but I'll get to this point later on. The point I was trying to make with these two slides is that, the naive scaling works. We get the right size objects, the right mass for both of these objects, so it works very well. Now, if you want to take it one step further and really calculate one of these curves and make a more accurate prediction, what you would need to do is to solve the Tullman-Oppenheimer-Volkov equations, also TOV equations, which you essentially get, so this is the Newtonian gravity result, which is just balancing pressure with Newtonian gravity, and if you're doing this within GR, then you get some corrections, which become important once the gravitational field becomes strong enough, and this typically is true for neutron stars, while for white dwarfs you can usually forget about these corrections. The second equation you get is for the enclosed mass, and you get the initial conditions. It's a coupled equations, two coupled equations. You set the pressure in the center of the object, and you solve outwards, and each pressure gives you 1 point in this mass radius curve. One important input that you have to give these equations is the so-called equation of state, which relates the pressure and the energy density. So here the energy density should be written as a function of pressure, and then you have just the pressure to solve for. And this really represents, the macroscopic properties of what you assume is an ideal fluid, that gets compressed in a gravitational field, and it represents essentially what you know about the microphysics. So, for white dwarfs, it's very simple. The energy density is... Yeah.
Sorry. In your P prime equation there, you have the Planck mass, which involves h bar. How does h bar get into this?
H bar is set to 1, as well as the speed of light, and everything is in natural units, so...
Still, if you have m over m Planck,
It's probably just G Newton.
Yeah,
Is that just-
Planck is one
That-
inverse
okay,
of G Newton.
But you just mean G Newton there, not M Planck.
Well, up to maybe some factor of square root 8 pi, they're the
Okay.
same to me. So,
Okay, that's, okay.
yeah. So for white dwarfs, that's a very simple equation of state. The energy density is simply given by the nucleon mass. So you need to take how many nucleons you have essentially per electron is something like 2 in light elements and multiplied by the number density. And the pressure is given just by the electron pressure, again, assuming it's a non-interacting Fermi gas, and you have closed form expressions for this, and you can numerically calculate it for every law, and then every number density and relate the energy and the pressure, so you get an equation of state. You can plug it into these equations and solve it. Okay, so this is all I have to say about stellar remnants. I'll pause for a sec if there are any questions.
So I would think that white dwarfs are under much, much better theoretical control, right?
You're
Because
absolutely right.
Right,
yes.
because this is just a plasma, a QED
Yes,
plasma
yes.
equation of
Which
state.
makes them a much nicer
Yeah, yeah.
system to study and to put bounds on, which makes neutron stars a much less
Yeah.
nice system, and I'll get to this point later. This is a Jupiter carved pumpkin from NASA. So now I'm going to talk about how we probe lighter QCD axions using white dwarfs. So what are these models that we're trying to probe, these lighter QCD axions? So our starting point would be just a typical coupling of an axion to the GG dual term, and I could just absorb this theta prime in A, but for now I'll keep it just for the following point. These interactions, once the QCD becomes strongly coupled, you get these non-perturbative effects, which generate a potential for the axion. And this is the form that it usually takes. And here is essentially the QCD scale in front, and I have this kind of suspicious looking epsilon in front. If you set epsilon to 1, then we are talking exactly about the QCD axion, and this is inverse F, which appears here, is just like the axion decay constant versus its mass, and this defines the mass of the axion, so it's just, you have a curve here when you set epsilon to be 1. Now there are two directions you can go in this plane. One is easier. Notice I didn't use easy, but easier is to make epsilon much larger than 1, and there have been some work on this where you can introduce additional contributions to this potential. The key point is that all of these additional contributions have to know somehow about this theta bar. Otherwise, you screw up the strong CP solution of the QCD axion. So there are a couple of models that are able to do that, so you just need to align the contribution. The other direction is harder, since you not only need to align it, but you also need to somehow cancel the QCD contribution, so the contribution coming from whatever other source you're imagining knows both about this direction and the size of this. Now there is a working example from Anson Hook from a couple years ago, and then there were a couple of follow-up papers from DiLuzio and friends where they really worked out all the details. So there is at least one working example of a model, a UV complete model that lives here. Naively, if you don't know anything about the UV, this looks completely tuned. But there is at least one working example where symmetries can get you there. And we're going to focus on the limit where this epsilon is much smaller than 1. Another consequence of this type of coupling is the fact that your axion couples to nuclei, and it couples in this very similar form with this cosine function. And in front you have a coefficient which has dimensions of mass. This is the sigma, known as the sigma term. It's very, very popular in nuclear physics. You can, in principle, measure it directly from pion nucleon scattering. You can also calculate it on the lattice. Interestingly enough, these two don't agree very much with each other, but everyone agrees at least about the order of magnitude of this. So we take it to be 50 MeV in this talk. So now I'm going to show you the same scheme that I had before, just for this particular example. So we have the axion potential, or this light QCD axion potential, and we turn on the background of our nuclei. Okay, and now we have the sigma term times the number density of baryons. And again, I took this limit of setting this to its background value. Once rho becomes large enough, and this would be increasingly easier when epsilon is small, then this potential flips sign at some critical density, which means that there's a new minimum of the potential form that pi f. This in turn means that you have now a nucleon mass that depends on the value of A, which was what we saw before, and now I'm claiming that there will be a region in space where this A would not be zero anymore, so the second term would not vanish as it does by definition, and you'll actually find a shift of about 30 MeV in the mass, a 3% shift, which at least when we saw this for the first time, we were like, okay, this would not do anything. It's just a 3% change in the mass. Why should it do anything? But it turns out there were some dramatic consequences, which I'll show you in a second. So now the question is, how does this back react? Now we have a Fermi gas with nuclei, but their mass is slightly smaller at some point in space. Does that make any difference? And what we find is that it does change the mass-radius relations. And what you would need to do is to solve these coupled equations together. Okay, we didn't assume one is a background and then check and neglect the back reaction. You really need to solve both of these systems together. So now, on top of the two equations that I had before, which were the Taube equation and this enclosed mass equation, we have first a correction to the pressure, which I will define right now. So we have the two equations from before up to this small correction here, and then this is just the field equation for the scalar. And the right-hand side of this equation is defined here as this u function, which appears also here, and importantly, it's proportional to the gradient of the field. So now, in principle, you can repeat the whole thing and set the pressure in the middle. The only tricky part is that solving this numerically is a bit annoying. And the reason is that you can imagine that the solutions of this axion field, of this scalar field, would kind of look something resembling an instanton solution. So you have something that's flat inside, and then there's a transition region, and you're going from one minimum inside to another minimum outside. And then in the Coleman picture, it's nice to think of it as the flipped potential. So you're going from one maximum inside to one maximum outside. And these classical trajectories are very sensitive to the initial value at the origin. You need to tune it just right, so the field ends up rolling outside and staying on this maximum forever, so you deplete its kinetic energy just as it reaches the top of the hill outside. So this is why it's a problem doing this thing numeric, or it's challenging. We did it, and it wasn't fun, but we did it. But we also realized pretty early on that there's a way to circumvent this whole thing by assuming that the size of the object is much larger than the typical wavelength of the field, the Compton wavelength of the field, which is now, in principle, a density-dependent property. So at each point in field space, you have a different density, which kind of fixes the typical scale of the field. But this condition is essentially equivalent to saying that the energy gained by the scalar going to a different place in field space is much larger than any energy cost you have when you're displacing the field, which is this gradient energy, or the energy stored in the wall of the bubble, if you want to think of it as a bubble. So this is essentially equivalent to this condition here, and it's also equivalent to taking f goes to zero limit. You can also think of it as a string that has a certain tension. This is the limit where the tension of the string plays no role in the system, and you can just, the field at any point can just take its value that minimizes the potential energy. And what this means effectively is that we can forget about all the terms that contain the gradient. This last equation becomes essentially decoupled from these two, and you can solve it for each value of rho. You would get a value for the axion field. And not surprisingly, this right-hand side is exactly equivalent to the requirement of minimizing the energy with respect to the axion field. So this is what you would imagine happen if you don't care about the gradient energy, is that at each point, for each number density, the axion will just go to the value which minimizes the energy. Yeah?
So I had the impression from a long, long time ago, like, you know, I'm thinking probably would be like in the 90s or something, Alex Kusenko looked at this problem for multi-field, you know, if you have some multi-field model, like the minimal supersymmetric standard model or something, and you're interested in tunneling solutions, it's very, very hard to do them numerically because of the reasons that you said. They're these very unstable solutions. But he found some way of just turning that into a numerically stable thing. So there was some trick where you can, you know, you have another set of equations that have the same solutions, but that are numerically stable. And I don't remember what the trick was, but
So we use the shooting method. We just
yeah.
tuned-
But I mean, no, this was
initial
supposedly to make it stable.
No.
So it's actually, these modified equations are super efficient. So I don't know, you might, if you're still doing this stuff, you might want to look for that
Okay.
paper. Yeah, Alex Kusenko, and like I said, sometime in the 90s, long, long time ago.
Right. Thanks. Good. So the effect of just solving this, in principle, decoupled from these two, is essentially equivalent to integrating out this additional field, because for each number density, I know exactly which value this field should take. So I can write essentially, you know, this field as a function of the number density, and then I'm back to having just the two equations. The difference now is that my equation of state is no longer trivial, but it actually encodes the effect of the axion field inside it, right? Since we had the axion both appearing as a mass dependence in the nuclei, you have this additional contribution just from the fact that you have this, it's almost like a CC, a cosmological constant-like contribution to the energy and pressure, which is these two terms here. So this shifts the energy and the pressure by the potential of the field.
So how accurate is this approximation?
How accurate?
Yeah.
This
Negligible
negligible
gradient.
gradient energy.
Yeah.
I'll show this in. I have the finite F result, so you can judge for yourself. But it works very well for energies. I don't know, below 2 or 3 orders of magnitude below the Planck scale. It's essentially irrelevant, all these effects. But you'll see it in a couple of slides. Good. So what kind of equations of state can we expect? Now it's very useful first to look at this left plot here is energy over number density. So this is like energy per particle on the y-axis. And on the x-axis you have the number density. So what happens is that below critical densities, which is the density where the potential flipped, you're just living in your usual, now it's phi, but it's a before, just the usual, you know, boring phase where the field is just at 0 and everything is essentially the same as a normal white dwarf. Then you hit this point and it causes an instability, which is shown here in dashed line. Now, how do I know that this is an instability and why this plot is even useful is because thermodynamics tells us that the pressure is proportional to the first derivative of this function. So you see whenever you have a negative derivative here, it means you're experiencing an instability. What it means is that if I set my system up here, it would naturally, without any other forces in the game, would want to expand and go down here, which means, not expand, collapse. It will go to higher number density, so this means this signals a collapse of the system. Here, you hit a 0 derivative or a minimum of this curve, which signifies that you have a new ground state. By definition, the only thing that is kind of interesting about a new ground state here is that it happens at non-vanishing number density. So you can think of this, for example, nuclei are also in their ground state, but they have some finite density. This is because you have a long-term attraction and a short-range repulsion, and then there is some sweet spot when the two of them are equalized, and then all the nucleons are sitting there, you know, 0 pressure, and they're just sitting there and chilling. So this is exactly what happens here. You have some balancing of these forces, and it's exactly the effect coming from the reduction in the mass as opposed to the increase in the decreasing the, essentially here it's just a reduction of the mass.
So does that mean that previously you did the simple estimate, neglecting the back reaction, and you got 30 some MeV or whatever?
Yes.
Is that roughly correct?
Yes, here it's exactly this 30 MeV. This is 30 MeV.
Okay.
Yeah, you have this instability here, and this is where you have a new phase emerging. The difference is that since this is lower than this, we would call this a stable branch, and this is called a metastable branch. In principle, you can live here as long as you want, but if at any point you hit an over-fluctuation of density beyond this critical value, you would undergo a collapse and a change in the phase transition. And this you have this branch here. And now if you really want to understand how the equation of state looks like, we can look at this plot here, which is essentially pressure versus energy. Here, this would be just the typical equation of state for a white dwarf. And the equivalent of this branch here, the stable branch, is appearing here. Well, up here, it looks again like a white dwarf. There's nothing really interesting going on here. But this is where, you see that there is a new ground state. The pressure can become increasingly small and goes to zero at some finite energy density. Okay? Now, if I take this and solve the TOV equations, I should get a mass radius curve. How would such a mass radius curve look? And how does it fit what we know about white dwarfs? So this is an example we calculated for one value of epsilon. This is a mass radius plane, normalized to kilometers and the solar masses. In black, you see just the typical white dwarf mass radius curve. And in orange is our model with some particular value of epsilon. I think it was 10 to the minus 10 or something like that. And here you see exactly the consequences of the structure I talked about a second ago, which is you have this metastable branch, which just follows the same line as a typical white dwarf. And then you undergo this instability. You have this blank space in the middle. And here is how the mass radius curve looks like for the stable branch. The reason why it goes all the way down here is exactly because you have this configuration where the pressure is very, very low. You can have a constant energy density object, and the curves here are essentially proportional to r cubed. So m equals to this epsilon star times r cubed. And what we are going to use to put some constraints on these models is the fact that our model predicts this big gap in the middle, which is completely inconsistent with what we see in observation. As you decrease epsilon, it would typically cause the gap to shift to the right. Brace yourselves. Here we go. Shift to the right. And and this is what I already mentioned as to why this mass radius curve goes all the way here. Now, this allowed us to put a bound on the epsilons just by the fact that we see things in this gap, which is between 10 to the minus 20 and 10 to the minus 8.
Sorry, but I'm really kind of confused about my earlier question now, because the radii, these quote unquote observed radii, are being inferred from a model that doesn't have these axions in it. We don't directly measure the radius. So
no, they do directly measure the radius.
Okay,
So we took data points that, to the best of our understanding, are an independent measurements of the mass and the radius that do not depend on any model relating the two. So
how do they get those quantities?
So as far as I understand, the mass is the easy part. Usually, if it's a binary system, that you
That's
can deduce
kinetic
the mass.
measurement. Okay.
And the radius, as far as I understood, is some sort of it depends on the luminosity. This is not trivial because these objects are typically not perfect black body, so you can't do it the usual way when you're doing luminosity through the temperature and surface emission and stuff like that. Then you have to go through another step which models the atmospheric effects and stuff like that. I'm saying this as a person that is not doing these things, but just trying to understand the best of how they do it. But as far as we understood, these are independent measurements of the mass and radius, because, as you correctly said, we want to test the relation, so we don't want to assume this relation when we're testing it. So it makes perfect sense.
Okay, thanks.
And then there's another parameter which I kept at 0 up until this point, but now I'm turning it off, for small enough values of epsilon, f, which was this decay constant, is the only scale that really determines where this gap sits. The intuition is such that f essentially fixes the size, the Compton wavelength of the field. So when f becomes larger, okay, then it means that you need to create a region inside the star that is both supercritical in its number density and it has enough size such that the Compton wavelength of the field fits inside. So if you increase f, you essentially make this transition happen at later and later points, and it pushes this whole gap to the left. And we had numerics that tell us where this gap is, and we had analytic estimates that we made with some simple toy models of toy models of these stars to understand how the scaling works, and everything seems to be in order. So this allowed us to put another bound for very small values of epsilon of these ranges in f, 10 to the 13 between 10 to the 16 GeV excluded. So this is how it looks in the plane of f versus the mass of the scalar. These two lines are lines of constant epsilon, which I just mentioned, and these two lines are the lines of constant f. The only place where you really need to do the numerics and solve the system for finite f to understand the bounds better are just these two corners here, which took like, 3 weeks to do just to get this little curve. Instead of, just two lines, it kind of curves this up and makes it smooth. So this is the bound we found. What happens in the rest of the parameter space? So here, white dwarfs would source this star, this scalar, but the stable branch reaches so far to the right and then turns back that it's consistent with all the observations. So what I'm saying is that in this part of parameter space, all the white dwarfs source the scalar, and they look perfectly fine, and everything is explained by the mass radius curves that are in this part. There's a region here where white dwarfs are just not dense enough to source the axion, so we don't have any constraints over there. And below here, white dwarfs are not large enough such that the star can fit inside, so this is just a finite f effect. When f is pushed to be around 10 to the 16, white dwarfs are just not large enough and the scalar cannot fit inside, meaning the gradient energy associated with this new phase is much larger than what you would gain from going to this new point in field space, in potential energy. And this is kind of a global picture taken from the unofficial PDG of axion limit due to Keir and O'Hara. So in this part of parameter space, it's essentially the strongest bounds to date. So this is all I have to say about this part. I'll pause for questions. Okay, these are, apparently there's white pumpkins, that's a thing apparently, and they're also very small, so it's white dwarf pumpkin. Next I'm going to talk about light scalars in neutron stars. So as was preluded a few minutes ago, neutron stars are quite different than white dwarfs, and one of the things that makes them very different is the fact that they are much, much denser, and the Standard Model is not well understood in these high densities. We don't have any working theoretical model that allows you to do reliable calculations above around twice nuclear saturation density given here. So all the theoretical frameworks that you can use up until this point kind of break down, and you can't really do anything until much, much higher densities where you can get some cool phases, which are probably not relevant for neutron stars. This is how the zoo of equations of state look. So you assume different microscopic models that explain how matter behaves at these very high densities, and each one of these assumptions will give you a different curve. And typically the name of the game is that if your curve doesn't go all the way up to these observed masses for neutron stars, then you're excluded. If you go up high enough, then you're fine, but there's no real reason why you would prefer this one over this one over this one. Typically because the radius is nowhere near as well measured as the mass. So as you saw before, you just have these blobs which kind of are compatible with almost every equation of state in the market. It also means that, as opposed to what we had with white dwarfs, what we're looking here is a large effect on top of big standard model uncertainty. So, if you're in a precision measurement and you're looking for small effects and you're trying to minimize your experimental errors and you're trying to look for something very small, the case here is that we're looking for this huge effect that's sitting on top of a large uncertainty in the standard model. So we're looking for a ginormous needle in a haystack. So we will not be interested in some order 1 effects, but only in very large effects. So how can such a large effect come about in these types of situations? So there's a very nice toy model that can explain how such a large effect can happen. So consider a pure neutron Fermi gas, which is actually a very good model. It's almost as good as any of the other models here. It's consistent with observation, maybe the fact that you don't push it up to 2, but order 1, it's kind of as good as everything here. And this just goes to show you that essentially the most important mechanism inside a neutron star is the neutron degeneracy pressure, and everything added to it is order 1 corrections to that. So if you just take the pure neutron Fermi gas, this is the mass radius curve. So yes, indeed, it doesn't go high enough. So in this sense, it's not good enough. But order 1, it's pretty much okay. And what you would find that if the neutrons were lighter, you would change both the mass and the radius of these neutron stars. And in particular, for example, if I set the mass to be just 3 times lighter, I would find an order 10 enhancement in the neutron star mass. So I can find a 7 solar mass neutron star. A 7 solar mass neutron star is essentially impossible to explain within the standard model. If we ever find an object through a merger or direct observation, which is not, point-like, which is not a black hole, it has a finite size, and is 7 solar masses, it will be very hard to explain using the standard model. This will be like a smoking gun evidence that there's something beyond the standard model. Because none of the standard model equations of state get even close to being able to explain something like that. So this is the type of effect that we would be interested in finding, in the sense that this will be the only way to really say something about beyond the standard model physics. Otherwise, order 1 effects are not really helpful where the uncertainty is order 1. So what we did for this purpose was to solve a more general system where we just added a field-dependent mass to our fermions, which were going to be our neutrons, to give the degeneracy pressure, and we have the potential for this fermion. Yes, so these two. Now, I'll typically use some dimensionless parameter theta, which is just pushing out some scale, and I'll use very harmless conditions on all of these. So I want the potential to be 0 at some vacuum value of theta naught. So this defines the minimum. This is the value of the potential in this minimum, and at this minimum, the mass of the fermion is whatever it is, m. It will be just the nucleon mass, let's say, we measure here on Earth. This defines your equation of state. You just have the Fermi pressure, the Fermi energy, and of course, important part is that you have this theta dependence everywhere. So far this is just a generalization of what we had before for the white dwarfs. This is where it gets interesting, because we're going to find qualitatively different things could happen. So one thing that could happen, which is what happens in white dwarfs, that if the reduction of the fermion mass is the most important effect, so it dominates over whatever contributions comes from this potential contribution of this cosmological constant-like contribution, what we get is this new ground state, which is exactly what we had before. We had this line here, the metastable branch, instability, and a new ground state here with this stable branch over here. This is what we had before for the white dwarfs, and if you think about it, it makes sense, because the potential energy was proportional to epsilon, and we worked in very small epsilon, so these things just were not important at all in this game. The other case would be if the potential contribution actually dominates over the change in the fermion mass, you can get this curve here in blue is a qualitatively different thing is happening. This is like a first order phase transition. You just have the 0 phase here, the theta 0 phase here, There's a jump in number density and energy density, but this transition is continuous for the pressure and the chemical potential, which is how you do it in first order phase transitions. So you need to do a Maxwell construction, and then you end up jumping from here to here once you hit the critical density. And this is what we call coexistence. The types of stars that you would get in this case are different. You would get a core in one phase and the outer part of the star in a different phase, as opposed to if you're living either here or here, you will have one phase inside the star. What does this mean for the equation of state? So this is again pressure versus energy. Typically, a new ground state would cause the equation of state to be what is known as stiffer, meaning that for a given energy density, you can support more pressure. Stiffer is kind of the direction that people in the equation of state community want to go, because this would allow you to support larger and larger masses for neutron stars. And the coexistence case, which is essentially, again, a first order phase transition, would typically make the equation of state softer. So for a given energy density, you can support less pressure. This would cause a reduction in how much mass can be supported in the star. And you see this discontinuity here, a jump in the energy density, but continuous across pressure. Okay, so this is the money plot for this work, and I'll build it up piece by piece, and it's going to be very busy at the end, but hopefully you can stay with me along the way. So I'm going to show you what we learned about almost model independent from our almost model independent analysis, and we have just two parameters in this game. One is the value of the fermion mass in the phase inside, which is this theta infinity that I have here, and the other one is the value of the potential at the same point. Now, the point of this being model independent is that the assumption is that you have one phase and then another phase. You have an immediate transition, and we're only probing these values. We don't care about the shape of this function around this value or the shape of this function around this value, just the values here. This works for the ALP model that we had before, where the potential just flips. And you can think of other models where it might be usable, but this is in principle why it's not really a model-independent analysis, but almost model-independent analysis. And everything here is in the negligible gradient limit. So the first thing we have is a line which defines which part of parameter space you will find a new ground state, and where you would find this coexistence state. Typically, we wouldn't care so much about what's going on here, because it would only make our equation of state softer, so our neutron stars would be lighter, and this is the wrong direction compared to what we want to go. In principle, you can use this to rule out maybe some parameter space, but we're still using essentially a very simplified model for the neutron star, so we're not going to take it that seriously. There's one part of the parameter space where we cannot really reliably say that you can do a jump from one value to the other, and you would unavoidably start probing the shape of these potentials and this function. So we're kind of putting it out of the game. And here, neutron stars would actually not source, would not be dense enough to source it. So to source the scalar field. So this is also out of the game. Now we can look at this plane and ask, where do our models sit? So the QCD axion is still somewhere over here. The light QCD axions do not change how much you reduce the nucleon mass, but you are tuning this epsilon parameter and taking this parameter to be smaller and smaller, and this is where we were with the white dwarfs. And it makes sense that below a critical value for epsilon, in this case, for example, here, you would change from the coexistent phase to the new ground state. We took some benchmark models here. We just stabbed 2 points into parameter space. We didn't feel very nice doing it without really giving some sort of toy model to really populate this space. So we have in our appendix a model which allows you to probe this part, which essentially changes the mass of the nucleon by larger amounts. And you can do it by coupling it instead of GG dual to G squared, just the field strength of the gluons. It's not completely trivial that you can really go to these low scales here, and it might require some tuning. Interestingly, there was a paper, I think 2 weeks ago already, by Hudson Hook and a student of his, where they used a similar coupling to try and solve the dark matter kind of resemblance in the relic density is factor of 5 dynamically. So they actually had this type of coupling, which I think was an interesting coincidence. Now we solve these top equations, and here I'm plotting curves of constant mass for this most massive configuration at each point. And you can see that, as expected, when the mass becomes smaller, you get larger and larger masses. The same goes for the size of the object. A smaller and smaller mass becomes larger and larger. If you're living on this line, it was exactly this toy model that I had. On this line, it's just a Fermi gas that has smaller and smaller masses. There's a similar kind of toy model that you can do to explain what's happening on this axis, where the mass is essentially not important, and you just play with this CC-like contribution. And as expected, or it's not as expected, but what we found was that there is a part in parameter space where you can get very, very different objects and very large objects, which will be very hard to explain using just standard model physics. And here I'm plotting, these are lines that we just wanted to get a handle of how high this F scale needs to be in order for our approximation to be valid, and we find this very high value. So essentially everything below 10 to the 18 GeV here, this approximation works. And just comparing the size of the object with the Compton wavelength of the scalar. Good. So now let me show you a bit of mass radius curves. So here you can see the QCD axion, as we said, is sitting here in the coexistent phase, and this is exactly what you see here is the first order phase transition, this jump here, and the object is not as massive as what you get from a typical Fermi gas, which is what we expected to find. These two curves here are in the new ground state phase. This is very similar to what we had for the white dwarfs. You see the gap here, and these objects can in principle become more and more massive the larger the change in the nuclear masses. And here, just for reference, we plotted just two observations of neutron stars just to see where these sit in comparison. And here, this is the most massive neutron star that was measured to date. Everything here is still in the negligible gradient limit. It was so much work to calculate the finite F result that I couldn't not show these as well, and this will go on to your question how well this approximation holds. So this is two mass radius curve plots at finite F for the QCD axion and for one example for the light QCD axion. And what you will see is as you turn on F and you take it from smaller values and increase it, this will typically delay the point where the instability happens. This makes sense. You need to generate a large enough supercritical region inside, and then you can also have some effect on the structure inside until it's so large that you don't really care, and it's so dense that you don't really care. And here you see similar things happening with the point of instability. As you increase F, it typically makes the instability happen at larger and larger densities when the size inside is comparable to the Compton wavelength. Yes, and you see also, of course, as you reduce F, you slowly converge to the limit of 0F that we have here in dashed. Good.
Sorry,
Yeah.
I didn't understand. So I thought you were telling us how good is this zero gradient limit.
Yes.
So I would want to see two curves, one of which uses the approximation and the other is exact, and they are close to each other. So what curves are those that are...
Yeah, so the dashed one here is the result at 0F, here and here.
Yeah.
The blue one here is the lowest we could push it numerically, and it was in a very good agreement with the 0F result. They're on top of each other, as you can see.
But for larger F, the colored ones...
And for larger F, you start seeing larger and larger deviations from this curve. The same goes here. It was just numerically more challenging to push f to even lower values so you can see the agreement better. So they're not lying on top of each other, but at least the trend is clear that you're approaching the 0f limit.
Okay.
It was harder here numerically to get to low enough values of f.
Okay.
It just means that the integration needs to be you have this very large separation of scales in the system, and it gets hard to do this numerically.
Right.
But yeah. Few last things I wanted to say before moving on to a couple of last slides. Let's see how am I doing with time. Okay, I'm kind of wrapping up, so that's good. I just wanted to mention that we did in this paper about the neutron stars, we also checked on top of these QCD axion-like models, we also checked the linearly and quadratically coupled cases, which were kind of easily reduced to simpler problems. The linear case was already done, actually. They beat us to it by a couple of months by Gao and Stebbins from Fermilabs, I believe. Unfortunately, the linear case is not so interesting because you have very strong constraints from fifth force, so it's not such an interesting model as far as probing new physics with stars. The quadratically coupled one is more interesting since the limits are weaker, and we had this analysis done in the paper. And another interesting thing we found when we were wrapping up this project was that this sort of theory with the field-independent mass can be directly mapped to these scalar, so-called scalar tensor theories that was proposed first by these folks in the 90s, and people have been working on this for since then. And these models are essentially ones where matter couples to gravity, not in the usual way, but in this weird way where you have an effective metric that you can write as some function of a scalar field times times the metric. And this function here can be just mapped to the mass that we had in the couple of previous slides by using this kind of conformal dressing field redefinition. So you can roll this function into the mass of the fermions. So this kind of, it connects our work to this other community. And what is interesting, I think, is that at some point they were also starting to look at stars and generating these mass radius curves, and they really didn't have a good understanding of why they are getting these weird shapes. While we understand what we're seeing, for example, in new ground states, we understand why the curve behaves the way it does, while for them it was just something the numerics popped out, and they didn't really have a good physical understanding as to what is going on, which in our equivalent picture has a much clearer interpretation. Okay, so that's all I have to say about light scalars in neutron stars. I'll pause for any questions. Yeah?
So, tell me if I missed something important, but you were talking about how because we don't understand a lot of these, like nucleon, right? But if the effect has to be that big, why wouldn't we have already seen it in a particle collector or something like that?
So the question is, why wouldn't we have observed already a neutron star that is 10 solar masses?
Well, if there is some beyond the standard model physics that can make a neutron star like wildly bigger,
Yeah.
wouldn't that have other effects somewhere else in some other physics?
And the point is that these will be very light and weakly coupled fields.
Oh, okay.
So this is what we have to deal with, and there are ways of probing it, but it's not in colliders. It's very hard to see them.
Got it. Okay,
But
thanks.
other ways you can see. Thank you. Yeah.
So, I know I still don't, I'd like to sort of understand better why why you're so sensitive to these energetics, okay? So, as you said at the beginning, as far as an effect on the nucleon mass, it's a few percent effect, okay?
Yes.
And there's no way these models, if you just put in a different nucleon mass of a few percent, it wouldn't change anything, right? Probably within the uncertainties of these models.
Yeah.
So, but somehow this is back reacting together with the scalar energetics, okay, in a way that suddenly there are entire swaths of of the radius curve that are just made unstable. So somehow the stability of these things is very sensitive to these
Right.
energetics, which are a tiny fraction. So can you explain that in a more intuitive way? What is it have to do with the fact that somehow it's probably important that we're balancing this against gravitational gradient energy, which is really small on the microscopic scale of things, or not. I mean, like, for example, I could ask the question, what about ordinary matter? If I just managed to make some non-gravitational ordinary matter, I just managed to make it very dense, would I suddenly make that unstable? I'm guessing not.
Not. So
Right?
this,
but it has
this,
to do with the gravitational...
So this has to do with the gradient energy. This was already pointed out by Anson and Wang when they had this paper in 17, which I have in my conclusion slides. They had something similar setup. The point is that nuclei are too small to source the object just because the scalar doesn't fit inside. So you have, they are metastable in principle. You just cannot, you cannot fit the scalar profile inside. So anything smaller than stars would be completely, you would never see a small object source in this scalar field. So this was the last part of your question.
So you're just saying that the Compton wavelength, or sorry, not Compton, well,
yeah,
just
the
the wave,
effective Compton
the Compton
yeah.
wavelength of these
Yeah.
things is so huge
Yes.
that you wouldn't get this effect
Correct.
in a small...
This was like a feature in Anson's paper, and it was so just
Sure,
one,
so this
which
is like this fuzzy dark matter-ish regime, but now for stars instead of galaxies.
And about the first part of your question, which is something that we didn't understand at first why you're so sensitive to this very small change. I mean, I think one intuitive way, at least in the in the plot, to understand why do you generate this big gap
Right.
here is just from the fact that for a white dwarf this is very, very flat. The only reason why this plot ever gets higher and higher are relativistic effects, which are very small in this case. So this thing is kind of very slowly increasing. On the other hand, the reason why this thing shoots up, and it unavoidably shoots up at small enough number densities, is this is exactly the effect of the cosmological constant contribution. It just looks like a constant over rho, and this one shoots it up. So you're kind of balancing this very small increase with this shooting up of the energy density, and this causes essentially this part here to be essentially quite large, even though the change here, between here and here, is exactly this 3% I was talking about. But I don't know if it really helps. I know that it helped me a bit to get intuition about what's going on.
So sorry, just go back to real basics. So the fact that that curve there is flat, this is the energy per particle as a function of the particle
Yeah,
density.
so this you need to switch
And
by
so-
rho times m. So this is essentially m.
But so what is the flatness, physically, what is the flatness of that saying?
It means that it's
Thermodynamically?
non-relativistic. It's just a constant up to relativistic corrections, which are suppressed by p over m, which is very small in a white dwarf equation of state. The only reason why this thing starts going up is because you start seeing either relativistic effects in the component. You just start seeing relativistic effects. So the fact that epsilon is not longer just the number density times the mass, but now it starts being, increasingly more relativistic.
So maybe another way, I'm sorry, but kind of pursue this a bit. So maybe another way of asking the question is that, okay, so now with this new scalar degree of freedom, you have the sort of freedom to turn on the scalar field and change the nucleon mass by this number of whatever it is, 30 MeV or whatever it is, okay? And so that certainly will change the energy, right?
Mm-hmm.
But then, I guess then the question I have is, why does it have such a big effect on the density? Is that effect, let's see, the number
So the
density?
fact that these 2 points are not very close to each
Yeah,
other
exactly.
is
What-
just because this thing is very slowly increasing, I think. So you just have to, that's my intuition. I don't know if it's helpful, but
Okay, okay.
the
Well,
only thing that helps you kind of balance out, the fact that you have a slope, a force in this direction is just the effect of the Fermi degeneracy pressure of the nuclei, which initially is very small just because they're very non-relativistic. So it kind of means that the short distance repulsion takes a long time to kick off. because you need to get them much, much closer for them to feel repelled by each other, just because it's an effect that's coming from the relativistic, the fact that it's a relativistic gas. This was a non-relativistic gas, you're essentially sitting at the zero pressure as far as the eye can see, and then at some point when relativistic effects become important, then you can really start seeing that this is a degenerate Fermi gas. But it takes a long time, so you need to squeeze them very much together until they start repelling, which is where you would kind of sit once you balance the effect coming from the CC that shoots up here. I think that's also a way to understand it. But just it takes a long time with the number density, just because it's so non-relativistic. You need to squeeze it a lot.
But if there's a phase transition, you should expect a jump, right?
Well, I'm just surprised that something that has such small scales in the energetics makes, a huge range of the radius.
We were also surprised.
Unstable, right? And so I'm just trying to thermodynamically unstable, right? And so I'm trying to
there's a
trying
big
to
gap
understand that
between
intuitively.
10,000 kilometers and 10 kilometers. That's another gap, right? And you go past, it's stable, stable, stable up to some critical mass, and then there's no more stable stars for white dwarfs beyond a certain 1.4, right? It just jumps up to.
Yeah, but that number is not very sensitive to, like, there's a bound like that, but then if I change the nucleon mass by 3%, that number just changes by like 3% or something, right? It doesn't jump by some huge amount if I change the nucleon mass a little bit. So generic 3% changes of this or that parameter that goes into a generic stability analysis will just change the answer by 3%.
Sure. We were also surprised.
Yeah, so I'm not disbelieving it, it's just I would like to understand this effect a little more
So
intuitively.
you're changing it from no phase transition to a phase transition.
Let's finish because there's another, the room is used as street.
Oh, okay, yeah, that's
Okay,
true.
So let me,
Sure.
yeah, we can also talk about it. Okay, then that's a pumpkin in space. Now, in the interest of time, I would really flash through these last two slides. I just wanted to mention that we had earlier work where we studied the QCD axion, not the lighter version, but the actual QCD axion at finite density. It was kind of an exploration of the properties of the QCD axion at finite density, which for us seemed to be something that people haven't considered in the past, so it was an interesting thing to see what we can say about it in Carrier perturbation theory for low densities, and the extremely high densities where people think that there could be this exotic color flavor locking phase. Unfortunately, it's probably at too high of densities to really be applicable in neutron stars, so we were trying to kind of catch this thing from both edges and get from low densities to very high densities. The problem is that in the middle, none of these frameworks really make sense, but we're hoping that at least qualitatively we're able to say something that is somehow useful. I think one of the most interesting things we found was that in one particular realization of the QCD axion, the coupling to neutrons is parametrically suppressed compared to the proton one, just because you have this accidental cancellation between some ratio of couplings and the ratio of the up and down masses, and you get some almost more than one order of magnitude suppression. But this cancellation only holds at zero density, and once you start turning on the background, then this cancellation gets messed up, and you can get a large increase in the coupling of the axion to neutrons, which is interesting for cooling. So in principle, I think one of the most interesting results here is that we found that there could be another order 10 uncertainty on cooling bounds in this particular case. And the second work I wanted to mention was that we used similar machinery to put constraints on relaxions. Now, the thing that makes relaxion different than anything we said so far was the fact that relaxion have also a tilt in their potential. So if you somehow get rid of this barrier, the field can roll to a new potential and a new minimum, and this new minimum is actually preferred also outside of the object. And then the bubble that is formed inside the object can just expand into infinity and generate phase transition in the whole universe. So this is really like, you have a seed something that seeds a phase transition because of its overdensity and causes a phase transition in the whole system. So this is what we use to put some constraints on relaxion models, which I'm just flashing here, and we can use different types of objects for different parts of parameter space. And the requirement was just that the change in the CC of the universe would not exceed a certain amount, and we relied on some other people's work here that assumed some cosmological model where you had some exotic dark energy that was available at some point in the past and then disappeared. So this looks like a jump in the cosmological constant, and we could, we took the result that is, irrelevant for essentially star formation, and this is what we used here. Good. So this is just, I wanted to very briefly mention them. And then our last pumpkin for today, I found this online, and I thought it was cute initially, and it says tag an engineer. And then I thought about it a bit more, and then I realized that I'm me, and probably some of you as well, if I had to write what does pi square is equal to, I would actually write 10. So 9 is a pretty good approximation.
That's G.
Sorry?
9.8.
That's G.
No.
Yes.
I think it is.
Yeah, that's G. It's
Why?
going to be G.
Oh, really?
9.8 in meters per second.
Yes.
Ah.
Meters and seconds, right?
No way. I see. Okay, but then it's a pretty good approximation then.
Yes.
Ah, nice. Cool. I thought it was 9. Tag an engineer, anyway.
You're not an engineer.
Sorry?
You're not an
No,
engineer.
I'm not an engineer. I'm
We
sure
are.
it was 9. Interesting. But now I see, yeah, there's a little thing here. No, that was too cute. Alright. So, let me sum up. I've showed you some new constraints we had on light QCD axion from white dwarfs. We talked about how scalar sourcing in neutron stars could lead to, in principle, very large effects on their mass radius relations, much more than order 1. QCD axion, I just mentioned, it could be sourced in principle by neutron stars. This was one of our results. I didn't even mention it, but this was one of our main points. But as I said, it was in frameworks where their usability in this range of densities is not clear. So, it makes our statement a bit softer, but still, I think it's an interesting result. And I just mentioned also some bounds on relaxion that we found by the effect that these bubbles can be seeded inside stars and then escape to infinity, causing a late time change in the cosmological constant. What can we do going forward? So there's a work coming out of Munich which would be a much better systematic calculation of the density-dependent QCD axion couplings, and there are people that dedicated their lives to writing down chiral perturbation theory at finite density and calculating as much corrections as they can as you push the density forward. But this could get pretty complicated at some point, so it's been a while. It's taking some time, but it should be out soon. One big question is how can we observe these axions or these scalars if they are sourced inside stars? I mean, one of the earliest papers on this was exactly by Hook and Wang, where they use these tails to probe long-range forces in spirals. But one could also think about if there's any observable effects with electromagnetic fields outside. The only problem there is that it gets complicated because electromagnetic fields outside neutron stars are complicated environments. If you let the whole thing spin, it also complicates things, but there could be also interesting observable effects, and it's a direction that we want at some point to pursue. It's very interesting that the future is kind of bright for anyone that's interested in neutron stars, just because we're going to have many probes in the future. If it's gravitational waves that we already see from mergers of neutron stars, that will start filling up this mass radius plane with better and better measurement, at least for the mass. And there are also programs that are focusing on neutron star observations. So this is the nicer telescope on the International Space Station that was supposed to be an 18-month project, and it's running till this day, I think like 6 or 7 years later, so I guess it's going well. Yeah, and then if I'm going back to where I started this whole talk was kind of the philosophy of checking using environmental effects, you can also think about if there are any other interesting environmental effects coming from the standard model, whether it's electromagnetic backgrounds or even gravitational backgrounds, and seeing if there's anything to be said about how this would change the beyond the standard model fields, and if there's any visible back reaction, you can kind of try to think about if you can come up with any other interesting things there. And yeah, that's all I have to say today. So thank you. I'll be happy to answer any more questions if there are any. If there's any time for it.
So LIGO's only found 6 neutron stars?
Yeah, I think there weren't, so I don't know how this
They
should.
found 3 in the first 6 months
I
and
think I
3
stole
since
this.
then.
I stole this from an older talk of someone, so it's probably out of date. Yeah, but it was like order 10 mergers, I guess. This 5 months.
So, do you know why you don't see white dwarf mergers? Since they have the same mass, have the similar signal.
I would guess that since they're larger
Or
and
it's
less
just 'cause
compact, I think they will be in a different
Different wavelength
regime
frequency.
or frequency. Yeah.
Did you look at the bounds from LIGO tidal deformation stuff?
Yeah, we tried having a look at this. I remember we didn't get very far, but we did look at this at some point. Yes, I remember getting into all of these love number business. And, yeah.
So Javi got bored with it and said,
Yeah.
let's move on.
Yes. Well, I think Stefan was looking at it at the time. I think we just came to the conclusion that we don't have that our models would not predict any observable effect in the tidal variability. Yes, that was the conclusion. We tried to calculate it and we didn't find anything that was within the experimental sensitivity.
Okay, guess we should, if we have more questions, we can move out of this room. So, yeah, sorry. Okay.
Thanks.